So this is experiment 16, capacitance, the graphic calculations for part 1. If you don't understand how to do the procedure for parts 1, 2, and 3 of experiment 16, then refer back to our previous video. And so let's just go into this. If you take a look at the graph, then you should be graphing on the x-axis 1 over distance, which is 1 over meters, and on the y-axis 1 over voltage, which is 1 over volts. You should find that as you increase the distance between the parallel plate capacitors, you're also increasing the voltage. Remember that part 1 is where you only transferred charge a singular time to the parallel plate capacitors and then increase their distance and graph that out. So to do these calculations, we're going to use the equation, so we're going to try to find what the capacitance is, ultimately. But to do that, we first have to find what the charge is, and then we can relate charge to capacitance. Here's what that looks like. So capacitance is equal to charge over voltage. And then you can rearrange this equation to say that charge is really just capacitance times voltage. And then we have a separate equation which equals capacitance. That is that capacitance is permittivity of free space, which is a constant, multiplied by the area, which is the area of the parallel plate capacitors, which is also constant, divided by the distance between the two plates. So this is basically saying we do how easily the charge can move through air, multiplied by how much space it has to move over, divided by how far it has to go. And then if you take this and plug it into this equation, then you can replace C with that to say that the charge is equal to permittivity of free space times the area of the two parallel plate capacitors divided by the distance between them multiplied by voltage. So then going back to the calculations, if you want to find the charge according to the same thing we just did, we were dealing with distance and voltage. This is meters and this is volts. And conveniently, the slope of our graph gives us meters per volt. So then if we plug in, if we use the same equation that we had up here, then we can then do the permittivity of free space times the area divided by just our slope, which is already meters per volts. So then you plug all that in with your numbers and you get some number which is in coulombs. And then now we want to take what is a number in coulombs of charge, and we want to translate that into capacitance, which will be capacitance 1, which we're going to use later. So capacitance 1 should equal the charge times our y-intercept. Now, that is because if you look back at this, then capacitance is charge over volts. And our y-intercept is, remember over here we had 1 over volts, so our y-intercept is just 1 over volts when you don't have to deal with distance. So then we're really just doing capacitance equals charge over volts, but then multiplying to get rid of the volts part. Or, we're doing charge divided by volts. My mistake. And then that will give you a number in farads. And this is a number that we're going to be using later on.